Tonight, evacuations are underway. A stretch of Southern California coastline has been shut down, and the danger is not over. Along the cliffs of the Palos Verdes Peninsula, rocks are still breaking loose and sliding into the sand below. What looks like a sudden landslide on the evening news is actually something far more unsettling. The visible surface of a much deeper problem that has been building for decades. At first glance, Palos Verdes appears untouchable. The peninsula rises confidently above the Pacific Ocean, just south of Los Angeles. Ocean views stretch endlessly into the distance. Luxury homes sit calmly along the cliffs. Roads curve neatly through manicured hillsides. Everything about this place suggests stability, wealth, and permanence. To the casual observer, this coastline feels carved from solid stone, ancient, unmoving, eternal. But that sense of permanence is an illusion. Beneath this postcard-perfect landscape, the ground is not resting. It is moving, not dramatically, not violently, but steadily, quietly, constantly. Entire neighborhoods in Palos Verdes are built atop one of the largest active landslide systems in North America. And most of the people living here have no idea. This is not a sudden disaster unfolding in real time. It is something more disturbing than that. A slow-motion collapse that has been unfolding across generations, so gradual that it fades into the background of daily life. The land beneath Palos Verdes has never truly been stable. It has only been pretending. And the most dangerous question isn't if it will fail. It's how suddenly. Because if this creeping motion ever accelerates, if millions of tons of earth were to break free at once and plunge into the Pacific, the consequences would stretch far beyond cracked roads or damaged homes. This coastline could become the source of tsunami. Not science fiction, not exaggeration. A scientifically plausible outcome based on real measurements. Real measurements, real movement, and real geological risk. Chapter 1. A peninsula that never stops moving. Palos Verdes feels timeless. Its cliffs seem immovable. Its neighborhoods feel anchored into the bedrock. But geologists have known for decades that this land is anything but stable. Unlike isolated landslides that occur after a heavy storm, Palos Verdes is experiencing something far more complex. A connected, large-scale landslide system where entire sections of the peninsula are slowly sliding toward the ocean. This movement doesn't announce itself with explosions or collapsing buildings. It reveals itself quietly. Roads that no longer line up, sidewalks that buckle and twist, utility poles that tilt at odd angles, foundations that crack not from earthquakes, but from the ground beneath them stretching and shifting. In some areas, the land has been moving continuously for more than 100 years. That slow pace is what makes it so dangerous. Gradual motion masks accumulating stress, like compressing a massive spring. Everything looks fine until the threshold is crossed. And when that happens, the shift from slow creep to rapid failure can occur without warning. In recent years, scientists have begun to observe signs that parts of the peninsula may be entering a more dangerous phase, one where long-term movement gives way to instability. The land isn't resting, it's loading. The instability of Palos Verdes didn't begin with modern development. It began thousands of years ago. The peninsula sits atop a prehistoric landslide complex formed when massive sections of coastal sediment collapsed under gravity, erosion, and seismic forces. Over time, vegetation reclaimed the scars. Soil accumulated. Human development smoothed the surface. The danger faded from memory, but it never disappeared. The most infamous section is the Portuguese Bend landslide complex, one of the largest continuously moving landslides in the continental United States. First formally documented in the 1950s, this massive zone spans several square miles, and it has never stopped moving. Sometimes the motion is so slow, it's barely noticeable. Other times, it accelerates dramatically, especially after heavy rainfall. In recent years, certain sections have been measured moving several feet per year. Pavement splits apart, sidewalks tear in half. Entire roads become unusable despite repeated repairs. This isn't surface erosion. This is an ancient geological structure reactivating itself. What's happening today is not the beginning of a landslide. It's the continuation of one. The geology beneath Palos Verdes is a perfect recipe for failure. Much of the peninsula is made of soft sedimentary rock, shale, siltstone, and clay-rich marine deposits. Compared to hard igneous rock, these materials are weak, fragile, and extremely sensitive to water. Hidden beneath the surface are clay layers that act like natural lubricants. When rainwater infiltrates the ground, it reduces friction and increases internal pressure, allowing massive sections of land to slide along invisible planes of weakness. This vulnerability is amplified by the peninsula's steep coastal cliffs. For thousands of years, waves have undercut the base of the cliffs, slowly removing support from below, while gravity pulls everything above downward. And there's another factor, the Palos Verdes Fault, an active offshore fault capable of producing strong earthquakes. A major seismic event could destabilize slopes already near failure, providing the final impulse needed for rapid collapse. Earthquake plus landslide is not a hypothetical here. It's a compounding hazard when human activity pushes the system too far. Nature alone did not create today's crisis. Human development made it worse. Since the mid-20th century, Palos Verdes has been reshaped by roads, homes, golf courses, and infrastructure. Irrigation system leaking pipes, swimming pools, and stormwater. Runoff constantly introduced moisture into already unstable ground. Construction added weight. Excavation removed support. In some cases, stabilizing material was stripped from lower slopes, destabilizing everything above. Modern satellite monitoring now reveals what the human eye cannot: widespread, coordinated ground deformation across the peninsula. This is not one landslide. It's a network of interconnected moving masses, all creeping toward the sea in complex patterns. Attempts to restrain the land with retaining walls and drainage systems have often failed. What was once a naturally adjusting landscape has become an overloaded system pushed closer to its breaking point. Chapter 5. The Tsunami No One is Ready For. The most terrifying danger isn't the slow movement we see today. It's the possibility of sudden failure. Large landslides behave like loaded traps. Stress accumulates quietly until a tipping point is reached. Then motion becomes violent and unstoppable. A prolonged storm, a powerful earthquake, or internal structural collapse could trigger a rapid slide. If a massive section of Palos Verdes were to plunge into the Pacific, it would displace enormous volumes of water almost instantly. The result would be a landslide-generated tsunami. Unlike earthquake tsunamis, these waves arrive with little to no warning and strike hardest near their source. Communities like Redondo Beach, Manhattan Beach, Long Beach, and even the port of Los Angeles could be hit within minutes. Scientists can't predict when collapse will happen, but they agree on one thing: the risk is increasing. Climate change is accelerating the threat. Stronger storms mean heavier rainfall. Rising sea levels mean faster erosion. These forces don't reset, they accumulate. The land is sending a warning. And whether this slow-motion disaster becomes a sudden catastrophe depends on how humanity responds. Long before the first evacuation orders were issued, the land itself was already sending warnings. Not through dramatic collapses or sudden explosions, but through numbers, quiet, relentless data points streaming in from sensors embedded deep beneath the surface of the Palos Verdes Peninsula. These instruments don't watch the land the way people do. They measure movement down to millimeters. And in recent months, those measurements began crossing lines that engineers never want to see crossed. Ground displacement accelerated. Lateral movement increased. Slopes that had crept for decades suddenly began sliding faster, not inches per year, but inches per month. In some locations, the motion doubled, then tripled over a short span of time. To the public, the cliff still looked calm. To scientists, the peninsula was speaking clearly. And what it was saying was this: the system was changing. When monitoring turns into alarm. Modern landslide monitoring relies on a network of tools most people never think about. GPS stations anchored into bedrock. Satellite-based radar that can detect surface movement from space. Inclinometers drilled deep into the soil to measure internal sliding. Rain gauges tracking saturation levels hour by hour. Together, these systems form a kind of nervous system for the land. In Palos Verdes, that nervous system has been lighting up. Data from satellite radar interferometry, known as NSAR, revealed coordinated movement across wide sections of the peninsula. Not isolated failures, but entire blocks of land drifting in the same direction toward the ocean. That's a critical distinction. Isolated landslides can often be stabilized. Large, connected slide systems are far harder to control. When one section moves, it changes stress on everything around it. Engineers watching the data realized something unsettling. The peninsula wasn't just sliding. It was behaving like a single, massive structure under strain. And strain, once it reaches a certain point, does not release gently. Rainfall that tips the balance. Rain has always been the key trigger here, but recent storms push conditions into unfamiliar territory. Southern California isn't built for prolonged, intense rainfall. The soil types beneath Palos Verdes are especially vulnerable to saturation. Once water fills the tiny pore spaces between particles, friction drops, pressure rises, and gravity takes over. This winter, storm after storm rolled in from the Pacific. Atmospheric rivers, long, narrow bands of moisture, delivered days of continuous rainfall. Not enough to cause immediate flooding everywhere, but enough to soak the ground deeply and completely. That's the danger. Surface runoff drains away. Deep saturation does not. As the water infiltrated, ancient slip plains buried within the peninsula reactivated. Layers that had been stable under dry conditions became lubricated. Movement accelerated. In some areas, monitoring stations recorded motion rates not seen in decades. That's when authorities began to worry about more than infrastructure damage. They began planning for people. Evacuations on unstable ground. Evacuation decisions are never taken lightly, especially in wealthy coastal communities where homes represent life savings and generational wealth. But when movement rates increase, the margin for delay disappears. Cracks widened in roads overnight. Utility lines sag. Gas pipes strained. Homes built decades ago, never designed for moving around, began to show structural distress in several neighborhoods. Officials issued evacuation orders, warning residents that continued occupation posed a serious risk. Not because collapse was guaranteed tomorrow, but because if acceleration continued, escape routes themselves could fail. That's the cruel reality of landslide zones. The danger isn't just what happens when the ground moves, it's what happens when slow disasters train people to ignore until they're no longer slow. Infrastructure under silence. As the ground shifts, infrastructure water mains stretch into the ground. Sewer lines fracture, allowing water to leak back, worsening saturation, accelerating movement, and vicious feedback. Roads are resurfaced again, each time masking deeper deformation. Electrical conduits rip, fiber optic lines snap. Everything built on top of the peninsula assumes stability. The land is not. In some zones, maintaining infrastructure has become a confusing battle. Repairs last months, sometimes weeks, before deformation reappears. Engineers face a brutal reality. You can patch damage. You cannot patch geology. Why sudden failure is the fear. Slow-moving landslides are deceptive. They feel manageable, but they can transition into rapid movement when thresholds are crossed. That threshold could be triggered by many things. An unusually intense storm, a prolonged wet season, a strong earthquake, structural collapse within the slide mass itself. Once motion becomes rapid, control is lost. Entire blocks of land can accelerate downslope, disintegrating infrastructure and collapsing cliffs into the ocean. That's when the danger multiplies, because rapid coastal landslides don't just destroy what's on land. They move water. The mechanics a landslide tsunami. When millions of tons of earth plunge into the ocean, they displace water violently and instantaneously. Unlike earthquake-generated tsunamis that propagate across entire ocean basins, landslide tsunamis are intensely local and devastating near their source. They rise fast, they hit hard, and they give almost no warning. Historical examples exist in Alaska, Norway, and elsewhere where landslide-triggered waves reach heights of tens or even hundreds of feet near impact zones. In Palos Verdes, modeling suggests that a large, rapid collapse could generate dangerous waves affecting nearby coastal communities within minutes. Redondo Beach, Manhattan Beach, San Pedro, the Port of Los Angeles, places not accustomed to tsunami evacuations. places with dense populations and critical infrastructure. This is why scientists are alarmed. Not because collapse is guaranteed, but because the consequences, if it happens, would be immediate and overwhelming. A risk that grows with time. Climate change adds pressure to an already fragile system. Warmer oceans fuel stronger storms. Heavier rainfall increases saturation. Rising sea levels allow waves to erode cliffs higher up the slope. Each factor pushes the peninsula closer to instability. And unlike earthquakes, which release energy suddenly and then stop, climate-driven forces are cumulative. They don't reset, they build. What makes Palos Verdes especially dangerous is that its instability is quiet enough to ignore until it isn't. The land doesn't need to move fast to be dangerous. It only needs to move far enough. For the people who live in Palos Verdes, the landslide is not an abstract scientific risk. It's something they feel every day. Doors that no longer close properly, windows that crack without being struck, floors that slope just enough to notice when a glass begins to roll on its own. These are the quiet signs of a home slowly being pulled apart from below. Many residents have lived here for decades. Some grew up in houses now showing structural strain. For them, the movement didn't arrive suddenly. It crept into daily life so slowly it became normal. Until it wasn't. When normal starts to break. In some neighborhoods, the damage reached a point where routine maintenance no longer worked. Driveways were repaired, only to crack again within months. Streets were repaved repeatedly, each time splitting along the same invisible lines. Utility repairs became cons.